Hello everyone, I'm Blessed Echem and I'm a PhD student at North Dakota State University in the Smart Lab. My advisor is Dr. Armstrong Abwa, and I'm very happy to present our work titled PaveCap, a multimodal framework for comprehensive pavement condition assessment with dense captioning and PCI estimation. This work was funded by Upper Great Plains Transportation Institute, UGPTI, mm, under the grant Center for Transformative Infrastructure Preservation and Sustainability. Why do we even have to assess the pavement condition? Why is it important for us to know the condition of the pavement? Now, pavement condition assessment is very critical because it helps transportation agencies know how to prioritize um, the repairs on the road and know where there are distresses on the road and then allocate budgets or funds to help them repair the road. Traditionally, this pavement condition assessment process is done through manual visual inspection. So normally, pavement engineers will um, walk along the road and then look at the pavement and then record the distresses. However, this process is labor intensive, is subjective, and then inconsistent. Imagine if you have 1,000 kilometer stretch of a road and then you have to go there manually and then record the distresses and then keep track of all the distresses. And this is very also subjective because every pavement engineer will have his own way of assessing the pavement condition, and there is no consolidated way of going about this process. Now, because of these limitations, researchers have moved toward automated image-based assessment using like approaches such as machine learning, deep learning to solve these problems. Now, let's talk about the existing automated approaches that are normally used for this pavement condition assessment problem. So the first approach I'll talk about is the image processing techniques. And an example of image processing technique is threshold segmentation. For threshold segmentation, an image, which can be an RGB image or a grayscale image, is converted to a binary mask. And this is done by normally thresholding the pixels in the image into different values. The problem with image processing technique is not robust to listening conditions and even noise. So it's not able to generalize across different real world scenarios. Now let's move on to distress classification. For distress classification, the whole pavement image is being classified, whether it's a distress image or it's a non-distress image. For distress classification, the algorithms normally used for this approach is classification algorithms such as um, deep neural networks, DNNs, such as ResNet, VGGNet, and other classification algorithms. The problem with distress classification is it just classifies the whole pavement, whether it has a distress, is a distress image or a non-distress image, and it doesn't really tell us where the distress is located in the pavement. To solve this problem, researchers came out with object detection algorithm. So for object detection, normally the the area or where the distress is located is being specified. So we can know exactly where the distress is located in the image, not just the whole image, but we can know the distress, where the distress is located in the image. We can also know the distress type and also the bounding box coordinates. However, distress detection still doesn't tell us the geometry of the distresses, or let's say the cracks in the pavement images. It just draw a bounding box or a box around where the distress is located. We don't really know the outlines of the distresses, the geometry of the distresses, or the cracks. To solve this problem, the researchers came out with distress segmentation. So for distress segmentation, we are able to tell the outline of the distresses or the cracks in the pavement image, and also even know the distress type. In addition, based on this information, we can even estimate the cracks and other additional information about the pavement image. Now, let's talk about the limitations, or let's give a summary of the limitations of the automated approaches that we talked about. The problem is existing machine learning or deep learning approaches, such as classification approaches, object detection approaches, segmentation approaches, they all give out numeric outputs. For instance, for bounding boxes, we just get the bounding box coordinates, which is basically the x, y1, x2, y2 coordinates, just the top left and the top right coordinates of, let's say, where the distresses are located. For segmentation, you can just get the binary mask. But the problem is, pavement condition itself is inherently multimodal, in the sense that pavement engineers don't really care about the bounding box coordinates or values. They're more interested in the PCI, which is the pavement condition index, which is just a rating from 0 to 100 that tells or gives a rating about the pavement condition. And also, when the pavement engineer looks at the image, he's more concerned, or he gives a contextual understanding about the pavement condition in itself. For instance, when the pavement engineer looks at the image, he is more concerned about the severity of the distresses in the image. He estimates the PCI and other important information, and also some important additional information which the bounding box, just the bounding boxes and the segmentation marks will not be able to just give out. Also, stakeholders or non-technical folks are not interested in just the bounding boxes, coordinates, or the values of the coordinates. They want a descriptive test, or let's say a test to give us how the pavement condition even looks like. So the problem is, most work, as discussed earlier, most work treats the pavement condition assessment as a numodal vision only task, or a numeric only task. Also, for existing approaches, there is limited interpretability and also communication to non-technical stakeholders, because most stakeholders who are non-technical don't even understand object detection in the first place. So you have to communicate to them and give out textual descriptions of the condition of the pavement. In addition, there is no pavement dataset with both explainable descriptions and even PCI values that can help us even solve this problem. Based on a summary of these limitations, it means we just don't need images or visual signals for pavement condition assessments. We also need natural language to help in our analysis. This is because existing approaches just focus on using images or a single modality to solve this problem. However, there is a need to combine visual signals and natural language to solve this problem, and this is our core idea. Now, based on that, these are our idea and contributions. First, we created a new multimodal pavement dataset with PCI values, which is just a rating of the pavement condition from 0 to 100, bounding box annotations for distress types, structured textual descriptions, Secondly, we developed a PCR estimation network, a single shot PCR estimation network that detects distresses and directly predicts the PCI just from images. And for the second network that we also developed was the dense captioning network that generates detailed natural language descriptions grounded in Pavement images. Now, before I go into the architecture details, let me briefly describe the dataset and make how this dataset makes this multimodal framework possible. For the dataset, the dataset consists of a top-down pavement images from multiple cities, from Jefferson, Peoria, Washington, Illinois. And the dataset is made up of images with their corresponding PCI values. And the PCI values are normally in ranges from 0 to 10, 10 to 25, 25 to 40, 40 to 45, 50, 55 to 70, and all other ranges. Now, the raw dataset originally had only images and PCI values. But for a multimodal framework, we need richer labels, so we added spatial and textual annotations. So for the annotations, we first annotated the distresses using bounding boxes, and we did that using CVAT annotation too. For the distress types, we considered longitudinal cracking, transverse cracking, diagonal cracking, block cracking, potholes, and patching. For the textual annotations or the captions, we structured the captions into 4 parts. So we considered the overall severity of the distresses, the present distresses, the absent distresses in the pavement, and also the pavement condition index. The annotations were created by pavement engineering experts, and they followed a standardized template in going about this process. So this is an example of the data sets, of the descriptive data set. So as you can see, we have the bounding boxes, which is drawn around the distresses in the image. And aside the bounding boxes, we have the text, which is um, the pavement severity. We have the present distresses, you have the absent distresses, and also you have the PCI. So this is how the data set that is used in our method looks like. Since we are done with the dataset creation, let's start with the overview of the framework. So this is the overview of our PaveCap framework. So you have the pavement image, which goes through our PCI estimation network. The PCI estimation network estimates the PCI. The same image goes through the dense captioning network. The dense captioning network gives out a caption which tells us the severity and of the distresses present in the pavement and also the absent distresses. Now, based on these two outputs, we combine everything together and then get the overall captioning of the pavement condition. Now we can dive into the two different networks. That's the PCI estimation network that we developed, and then the dense captioning network. Now let's start with the PCI estimation network. For the PCI estimation network, we use object detection and segmentation to improve the pavement condition index prediction. So for the PCI network, you have the input pavement image with the distress and everything in it. Now we pass this input image to a YOLO V8 model. Now this YOLO V8 model has been trained on the pavement images with its corresponding bounding boxes. So this is the final trained YOLO V8 model with it has been trained on the distress types and their bounding box coordinates. Now we pass this input pavement image through the V8 model algorithm, which is an object detection algorithm, to detect the distresses. So it tells us where the distresses are located in the image. Now once we are done, we extract the bounding boxes as prompts. So we get the bounding boxes of the different distress types in the image. So we pass the bounding box prompts and also the input pavement image to segment anything model. Now segment anything model, which is called SAM, is a zero-shot state-of-the-art segmentation model which doesn't need training. So you can just give it the pavements and let's say add bounding boxes as prompt, and then it will be able to segment and tell you the distresses or where the distresses are located or outline the distresses in the image. And we do this because it's very difficult to get segmentation mask, and also sometimes the image or the pavement images or distresses which will be encountered in the real world are out of distribution from the training data that will be used. Now once we pass the input pavement image and bounding box prompt to segment anything model, we get the binary mask which tells us where the distresses or outline the distresses in the pavement image. Once we get the binary mask, we concatenate the binary mask and the original pavement image together. After doing the concatenation, we pass it through a convolutional neural network. The point of this concatenation process is to be able to retain both the rich features from the original pavement images and also the outlines of the distresses. The convolutional neural network then predicts the PCI for us, which is the rating from 0 to 100. Now, let me show you the training details and also the loss functions that are used for the PCI estimation network. For the PCI estimation network, we use the following hyperparameters. So we use, for the image resolution, we use 416 by 416. We use this so that it can help us get the right dimensions for the YOLO V8 backbone. We also use number of epochs, or we train the model for 1000 epochs. The optimizer uses the Adam initial learning rate of 0.001. We use loss functions of MSE, which is the mean squared error, and the MAE, which is the mean absolute error. For the network components, just the YOLO V8, the segment anything model, and the CNN, our full layer CNN. Now let's talk about the evaluation metrics for the PCI estimation network. For the PCI estimation network, the goal here is to regress a PCI score in 0 to 1 from an image, just from an image. And the metrics used is the mean squared error. And the mean squared error, the function of the mean squared error is to penalize large errors more during training. And it's also the standard evaluation metric for regression task. And this is the formula for the mean squared error. So it's just the sum, the average of the sum of the square differences of the different predictions. We also have the mean absolute error, which also is very interpretable because it just tells us how off our prediction is from the actual value. Our predicted PCI is from the actual PCI value. And there's the formula for the mean absolute error. Now we report mean absolute error as the main metric because pavement engineers really care about how the PCI is off from the prediction. Now that we understand the PCI metric, let's move on to how the second component works, which is the dense captioning network. So for the dense captioning network, we have the input pavement image. We pass it through the YOLO V8 backbone. The YOLO V8 backbone was extracted from the YOLO V8 model or algorithm which has already been trained on the pavement images to extract meaningful features. The reason why we're using the Elevate backbone is to get or to use the retained features from the Elevate algorithm. So we pass the input pavement image to the Elevate backbone to get the feature maps. And these feature maps are in 2D. So we flatten it using like adaptive poo and the flattened model to get 1D feature maps. So once we get a 1D feature map, we do this because the input to the transformer model is normally in sequences or 1D. So you have to make sure the 2D feature maps are converted to 1D before you feed it into the transformer encoder. Now we get the embeddings. We add position information. So we add positional encoding to this embedding so that we can give other information to the image embeddings. This is because transformers are naturally a permutation invariant and they have no other information. So we add this positional encoding to help capture other information. So we pass the image embedding to the transformer encoder, which helps us to capture global dependencies and like contextual information between the embeddings. We pass the output to a 1D feed-forward neural network. And the reason why we do this is to help capture both the global features and also help capture the local features also. Now, given let's say an input and the red embedding, we have the red embedding. Now we get the embeddings for the red embedding. We add positional information to the red embedding, and then we have the transformer encoder, which also encodes the information or helps also capture the global dependencies across different words or tokens. We get the output from the 1D convolutional feedforward network and we do a cross attention between the information from the image and then the text. We pass it through a linear softmax, a linear and a softmax, linear layer and a softmax, and then we get the output caption. So for the decoding process, the output or the tokens are generated one after the other. So it's basically a next token prediction task for the decoding process. So the tokens are generated one after the other. So once we pass the start of sentence token to the decoder, it generates the next word, and then till we get the final caption for the pavement condition. So let's move on to the training settings for the dense captioning network. So for the dense captioning network, for the image encoder, we use an embedding dimension for the visual tokens of 512. So that's the embedding dimension for the token embeddings for the images. For the transformer, when it comes to the text part, for the D model, where the vector dimension for the text, we use a dimension of 512. For the decoder feed forward dimension, we use 248. The number of decoder layers is 4. Number of decoder hairs is 8. For the training, we train the dense captioning network for 300 epochs using an early stopping patience of 50. And then for the learning rate, we use 10 exponent negative 4. These are the metrics for the dense captioning network. For the dense captioning network, the goal is to generate structured captions describing the pavement condition and the distresses. So we use different metrics. We use the BLEU metric, we use the BLEU metric, and we use the meteor metric. So the BLEU metric measures the n-gram overlap between the predicted and then the reference captions, and the BLEU measures just compares both the n-gram and the n-gram per section and then recall. For the meteor, it uses the precision, recall, and a penalty for the fragmented matches, and is normally correlated with better human judgments, and is able to capture synonyms and paraphrases better than the BLEU score alone. Now, with both networks trained, we evaluate them separately and then show how they work together. So I start with the PCI estimation results. For the PCI estimation results, this is the quantitative results for the PCI. So you can see for the image on the left, we have the prediction error. There's the predicted PCI minus the actual PCI. You can see most of our predictions was the model was able to predict most of the PCI. You can see for a prediction of 0, you are getting a very high bar or frequency for most of the like the results, and it's normally distributed. You can see the errors are concentrated inside the middle. It's normally distributed. So you can see the PCI model is doing very well across the different PCI classes. For the qualitative results for the PCI, these are some of the accurate PCI predictions, the on-spot PCI predictions. So the image on the far left is the original image. The column on the far left, the original image. The middle column is the bounding box predictions, and then the column on the far right is the zero shot mask predictions. And then we have the actual PCI, and then the predicted PCI. So you can see on the first row for the original PCI, for the original image, we're able to get the actual PCI prediction on spot. So the actual PCI was 4, the model was able to predict 4. And you can see the zero shot mask predictions where the segmented model was trying to segment or focus on. And for the second row, the model was able to also get the actual PCI value. So the actual PCI value was 8, and the predicted PCI value was also 8. So you can see for the second row, the image is alligator crack is concentrated at most parts of the image, and you can see the model was able to focus on that part and help it to predict the PCI. These are some of the accurate predictions for the same PCI estimation network. For the first row, you can see we are getting the accurate PCI of 38. You can see for this, for the first row, the model is focusing on the patch on the pavement and is able to focus on that and use that to help it in the predictions for the actual PCI value of 38. Yes. Yeah. Same for the second row. Now, nevertheless, some of the PCI values were slightly off. You can see for the first row, we had the actual PCI was 28, but the model was predicting a PCI of 33, and it was not able to also detect any distresses. So you can see the model is just focusing on the images and using it for predictions, because our SAM model was not able to get a segmentation mask, so you're just focusing on the image itself for the analysis, and that's one of the shortfalls. So you can see this one on the first row, it makes the PCI values by approximately 5 points, and we believe this slightly off predictions were some artifacts like the shadows that were not able to, the model was not able to capture or help, or it confused the model a bit as distresses. And also for the second row, the model was also able to predict the actual PCI, was able to predict the PCI of 48 while the actual PCI was 47. So it was slightly off by 1 point. Now let's move on to the quantitative results for the dense captioning network. So for the dense captioning network, you report the BLEU1 through to BLEU4, BLEU, and Meteor along with their standard deviations across the dataset. The BLEU scores decrease as n increases, right? So as the n grams like increases, like which is expected because matching longer n grams, the exact n grams, is harder, and also BLEU and Meteor are in the similar range, with Meteor around 0.32 on average. These values indicate that the generated captions have important or substantial overlap with the expert annotations, capturing both the key distress types and also the severity patterns. Now let's move on to the qualitative results for the dense captioning network. So for this slide, the first column is the original, consists of the original images. The second column is the attention maps, and the last column is basically the captions, where we have the actual captions and then the predicted captions. So you can see for the first row, you can see our predictions are on spot with the actual ground truth or the ground truth caption. So our model is able to capture the high severity block cracking, is able to also capture the high severity alligator cracking, and also all the absent distresses in the original pavement image. Also for the second row, our model is able to capture the high severity block cracking and also all the absent distresses in the pavement image. You can see the model is doing well in capturing the distresses. Now, aside the captions, we included the attention maps. And the purpose of the attention maps is to help in model explainability and also interpretability, because we want to know where our model is focusing on when generating the captions, so that we know whether it is doing the right thing or not. So it helps pavement engineers in interpret the models or what the models are doing, because most of these models are black boxes. So you want to know where the model is focusing on in generating the captions. As you can see, the attention maps are focused on the right places or the critical areas within the pavement image. This slide shows instances where the dense captioning network falls short. In one case, when you look at the first row, the model downgrades the severity of the alligator cracking or fails to even mention some of the present distresses. In the second row, it even misidentifies or omits the distress type. So it's not able to even tell us the low severity transverse cracking in the image and also the high severity alligator cracking in the pavement image. These errors often arise in borderline situations where severity is very ambiguous and where the cracks are faint and very difficult to distinguish from the texture. Interestingly, there are some cases where the model actually corrects annotation errors in the training data. So you can see in this example, the ground truth caption labels the image as having high severity longitudinal cracking, but in reality, we see high severity alligator cracking. The model's predicted caption correctly identifies high severity alligator cracking and lists the absent distresses in a more accurate way. This suggests that the model has learned meaningful visual patterns and can sometimes override noisy or incorrect annotations. Now, to better understand what drives performance, we also ran ablation studies. Yeah, so for the PCI expansion network, for the ablation settings, we compare two settings. So whether the inclusion of some or the exclusion of some will help affect the PCI predictions or the PCI results. So with some, we obtain a validation mean squared error of about 474. and a mean absolute error of 16.21. And without some, MSE increased. So it increased to 491.64, and MAE also increased to 16.43. Now, this improvement is very modest, but it's very consistent because it indicates that providing explicit segmentation mask helps the network make more accurate PCI predictions. For the dense captioning network, for the ablation, we examined different backbones and whether they were frozen or um, fine-tuned. So this table reports the BLEU, the GLEU, and the Meteor for various backbones. So we considered YOLO V8 through to YOLO V12, and also we also considered raw time detection transformers. Now, but the best performance which is highlighted comes from YOLO V8 with an unfrozen backbone. Now, that means fine-tuning the backbone leads to higher BLEU4 and also glue and meteor like compared to the frozen variants. But real-time detection transformers, for instance, underperforms in this setting, and suggesting that not all the detection backbones transfer equally well to dense captioning. Now let's talk about the limitations and future directions for the work. For the limitations, we only cover prominent distress types. We didn't consider distresses such as rotting, bleeding, shaving, and other distresses. But sometimes our approach becomes sensitive to the lighting conditions and also shadows in the pavement images. And the PCI errors also near category boundaries can still affect maintenance decisions. For the future work, we want to extend to richer multimodal tasks such as VQA, visual question answering, visual reasoning, visual grounding for pavement images. We also want to build larger and more diverse multimodal data sets and also explore advanced VLMs and also improved segmentation or attention models. These are also the practical implications and also the key takeaways from the work. For the practical impact, agencies can also get a PCI scores plus natural language explanations and to help better communication with even non-experts in the field. And also it helps in the improved transparency, interpretability, and also trust in automated payment systems because you're able to get interpretability or meaningful contextual understanding of the payment condition. It also helps in the potential to reduce manual inspection costs and also standardize assessments. For the key takeaways, we know payment condition assessment should be treated as a multimodal problem rather than a unimodal version only task or a numeric task. Also, PaveCap shows that combining PCI estimation and dense captioning is feasible and also effective. And finally, we know multimodal AI can bridge the gap between technical outputs and also human decision making. Thank you very much.